Hey, thank you. What a pleasure. So I wanted to give a talk that was about data wrangling and hacking in tools and some of the tools that we use in the Open CONNECTOME project. And the ability to develop software today compared to what I was doing 20 years ago at IBM is amazing, how agile it is. And the idea that you're all going to get together tomorrow without me, you don't need my help, and get lots done is spectacular, and only through the tools that are available. So I've been working on the Open CONNECTOME project for about 3.5 years. I was under the impression that, whoa.
Corners are hot.
I'm getting that.
There we go.
Can
What do you need?
just drag the middle down
Interesting.
so I can see my slides. Yeah, you have to grab the bar, pull it down. No.
I don't know how to use computers.
Hang on. No.
You do it.
All right. I was under the impression that I was doing this, which was working on starting with electron microscopy data, these really massive imaging data sets, and to build a data store for these data sets that would feed it to analysis tools, particularly things like high-performance computers, or now it's evolved to cloud tools and analysis engines like Spark and Thunder. This was great, and this is what I wanted to do, and this is what I sold, and this is sadly only my impression, because people do with your tools what they want to do, not what you want them to do. And what I found is that I've really built a platform that feeds two-dimensional tiles for visualization and human manipulation of data, regardless of whether I wanted to or not. So CatMade is a huge user. We've also now got a leaflet environment. And these are really beautiful tools to pan zoom, to have a map interface to data, to do some lightweight data manipulation, to do user annotations. And so this is a use case that I didn't design for, but I have to build for. And so what I have now is I have over here my Open CONNECTOME project, and that's my machine. My machine has 11 petabytes of data, of which we have about 500 terabytes now of brain imaging data in different modalities. And then we've got our visualization tools, and so how are we going to link this up? Well, the natural thing to do is to throw a web browser in there, throw an internet in between. That's an internet. It's actually a great picture of the internet. And then feed it tiles through web services. Right? And we did exactly this, and this is great. Except we have some system goals. And the system goals are to provide a good user experience on viewing tiles. And so this includes things like having some visual flow when you interact with the data. So that means providing, let's say, 18 frames a second. I'm not a human factors person. I picked this from a website that says 18 frames per second is visual flow, but it's at least 10 and fewer than 60. And some tolerable latency. So 100 milliseconds to first byte would really be ideal, and less than a second to stay within human patience and the perception of the system responding to them. And so for me now, this means I need to deliver something like 30 512 by 512 image tiles for each view, and this can be, because I have multiple layers, the layers are independent, I want to draw them over each other, and I can't do this at internet latencies. So if I try and plug the internet into the browser and put a web server on my server, I'm not having a good experience, or my users aren't having a good experience, which means I'm not having a good experience. So what we're going to try and do then, and the way to deal with this, and this is now standard internet techniques, is to push that data to the network edge, move it near the browser. And this is done through things like content distribution networks or internet cache hierarchies, and caching in the internet co-evolved for exactly this reason. So the first question is, can I do this with a content distribution network, which is how Netflix gives you all of your movies. So what Netflix does is they take a movie, they encode it in multiple formats, they shop that out to lots of content distribution networks. The content distribution networks push that content to your ISP near you, and then you access it locally at low latency you minimize the cross-sectional bandwidth over the internet, you're using fewer resources, and you get a better experience. And this diagram shows that you ingest the data gets pushed by this content distribution network out to a location to you near you in the network, and then you consume it locally. Now, this is great, but it doesn't match the type of data access patterns we have. And so what are those data access patterns? Well, the first observation is that we're not able to predict what data the user wants when they want it. We have really large data sets, so let's think hundreds of terabytes in very small regions of interest that are defined by the user and the user's interest. Not only that, our databases are not full of tiles. We store high-dimensional databases that are 3 or 4D spatial databases, and then we dynamically materialize tiles on demand for visualization. And these tiles may come from any one of the projection planes. So we don't just want to support along the slice dimension. If you want to look data in XY or XT for 4D data, that's fine. And so we're going to support these axis orthogonal cutting planes on demand. So we have to materialize the data the user wants when they want it, and we can't predict that. Not only that, we have other imaging data. So this is array tomography data, which I love. And I love it not because I understand anything about what's going to happen with the science on it, but because we have sort of 40 to 50 different channels from different antibodies. And these channels need to get accessed in interesting ways. And so I took this as a cut right from my website. And what it shows is we've got the same data set from Nick Weiler that was collected in Stephen Smith's lab. And in each one of these, this is the gateway to a visualization environment. You click this pane and you get a maps interface. Is that they're interested in looking at different combinations of 6 different channels from the same data set. And so if you say, oh, hey, your data task is to have choose 6 different views and to produce them on demand, then that's not a small number of options or a predictable set of data. And we also flatten them for performance dynamically. We don't send each channel independently. When you get a view of these data, we're going to take all the data and combine them into an image, false color it, and produce it so that we send less data as well. And so we conclude that not only do we have to push data to the network edge, but we've got to dynamically manage the data that's getting put there. And that means caching, and it means application-specific caching. And so here is where the data wrangling part comes. So let's get back to our internet. No internet picture anymore. So we're going to change the world a little bit, and we're going to have the same visualization client, my same petascale data cluster, and I'm going to add some technology. I'm going to move my web browser over here to the local network. So this is going to be a low latency network environment. And then I'm going to throw some disk drives over there, and this is going to be terabytes of disk drive. So this could be, it is my laptop. It also is a workstation in a lab, or it's a workstation in a caching gateway at the ISP level or at your network level. And so that'll be our web server. That web server is going to interact with the cloud on the back end. I'm going to have a memory caching cluster on the cloud as well. We'll show you how this all goes together. So now we're going to get the same tile request to the web server. The web server is going to access a web service to the back-end cluster and say, give me a tile. Well, the database goes in, and we use NoSQL databases. I support React and Cassandra and MySQL, but that's not really relevant for this. We go and we do an I/O. We access multiple nodes and get the data and materialize a volume of data, render the slice that's wanted out of the volume of data, and ship it back. And that's the way these viz tools work. You ship tiles, and everything's happy. Now, when we do that, we're also going to take a copy of that tile, and we're going to throw it in a memory cluster. And so now the memory state of the distributed system at the end of this request is we have a tile in the memory cluster, we have a tile and the cube in memory on the server. They're just in memory because we just access them. It's a happenstance situation. Now we're going to leverage that, and we're going to use some really fun tools. So this is Celery, and this is Rabbit. And Celery is a asynchronous scheduling framework, and Rabbit is an asynchronous execution engine. And so what this allows me to do is have my web server launch jobs that run in the background. So I've already delivered my tile to the interface. The user is happily panning and zooming, having that Google Maps experience. It's delightful. I love that experience. And what Celery and Rabbit are going to do is asynchronously make a request, and they're going to get that volume. They're going to take that volume and bring it locally, render it, and put it on this local cache. So now we've materialized a volume around the requested tile locally. Now subsequent requests come, and they just access the data straight from the local storage. And that's how we're going to get that user experience of visual flow. And this also, all the tiles are pre-rendered. There's no computation associated with it. You just access the tile from the cache and serve it up. So why do we have this memcached? Well, memcached is across the internet and is server side. So that's not really where we want to get data from, but there's a couple reasons. The first one is that this background loading is not necessarily instantaneous. And these visualization tools, particularly when you're working with slice interfaces, a lot of people like to click their scroll wheel and they'll build up 15 layers of requests and just want to zoom back and forth through a set of slices. A natural thing to do. This builds up this incredible queue of requests that hopefully we can serve in a timely fashion. But what will happen is before all the data can be rendered, you might revisit a tile. And we want to serve that out of memory. And so by putting the tile, rendering it, and putting it in memory cache, we get it without accessing disk drives on the server and without loading the server again. So this makes the resource more scalable. It also is important, well, so the comment here is you're not doing any I/O or any SQL queries on your cluster when you're accessing the data. The other thing is for data that you want to change, caching the data it's difficult to change the data and then materialize the changes in the viewer. And so there are interfaces where we don't want to use a local tile cache, and then memcached is very helpful for that as well. All right. So the so what here is this is when you build data systems, you don't get to build them the way you want. It's really disappointing or really delightful. And our goal here was to end up with local performance to remote data, which is absolutely necessary. We're getting to the point where the imaging technologies are such that you can't image and store the data in your lab and expect that to be successful, nor does that support the data sharing. And yet we want to preserve that user experience of having the data seem to be local, right? If putting your data on the cloud ruins your response time, it ruins your visual flow, then you're not going to put your data on the cloud, and we're going to deal with other limitations. So this is, for me, making data centers in the cloud useful. And really get that user experience where you get local experience. And it's not quite there. The way this works, and I can't demo it because I don't have a local cluster, and this is not my laptop. Thank you for not having my laptop, which means I don't have to demo. Is your user experience is that you scroll back and forth and it just all works, and every once in a while you hit a miss where the data you want is not local, and then you have 100 milliseconds or half a second to get back to that interactive user experience. And that's a pretty good user experience. It's not the same, but it's a lot better than what you get trying to access data just straight from the internet. So this is new. It's open source tile caching for any spatial data. We're going to roll it out for 4D data as well. And it's open source and freely available. And I do want to comment that it's not currently being deployed in any site that I don't manage. So it's at some of our collaborators' sites, at Harvard, at Allen. It's how we run all of our interfaces. But send me hate mail if you want to try and use it, and I will make it work for you.
Right. So apologies to any non-developers in the room, but why were you using two message queues, Celery and Rabbit, instead of just one?
So Rabbit is the scheduler, and Celery is the interface to it. So when you run Celery, you actually have to run a queuing system behind it. So Celery is not a queuing system. Celery is an interface to a queuing system. And so you can run Celery with Rabbit, or you can run Celery with, I don't remember what else, but you run them together. There's another question. But those are examples of developing that kind of software 15 years ago took months. You know, you'd say I want an asynchronous fetch interface for my cluster, and I wrote that in 2 days. It's absolutely amazing. Yes.
So the amount of data that you're wrangling right now, is it equivalent to the amount of data that human brains have to deal with on a daily basis, or is it more?
You've asked the worst question for me. No, the second worst question, right? The question that people like to ask me is, what's the comparison of the computational power of the human brain? And so I don't have a reasonable estimate to the amount of data that the human brain wrangles. I will say that the data capabilities of the human brain in terms of approximation and early filtering completely exceed the way that data management works in computer systems. And so the human brain distributes computing in layers and does data reduction and pushes lots of computation way out into the network in a way that we're not doing in computing. So anecdotally, I'm going to spend next year at Los Alamos National Labs working on their exascale architecture. And one of the biggest problems with exascale computing, so this is getting to an exaflop of computing integrated in one system, is power consumption. And the observation is the way that we compute today, where we take data and we move data to processors and we compute on it and then we ship it back across networks or to memories or to storage, we'll never get to exascale. There's just not enough power in the world. And the way to solve this is to start pushing computation, so you're doing computation at the disk drive, at the network interface card, at every layer in the memory hierarchy. And this is a very primitive way to start to model what the brain is doing in terms of distributing computation into its network. And it does it in, so that was an almost coherent answer to a question that I panicked about.
That was great. That was great. Thank you.
So how intense is the processing that's happening to go from the volume to the tiles on your local server? Is that something that you could foresee, like getting rid of the need to have a local server running, like through some technology like web workers or something like that? Or is it just, it needs too much power?
So let me make sure I understand the question. The question is, how much computation does it take to go from volumes to projections of the volumes?
Yeah, essentially.
Yeah, so it's not really a computation thing, it's a memory organization. In that the way to think about it is if you take an image and you take a very naive organization, so you lay it out scan line by scan line, top to bottom, and then you want to take a cut of that image, right? Just a vertical line through it. You're then getting 1 byte from every scan line.
Right.
And so that's very memory inefficient. And so the whole core of the spatial database is techniques that allow you to organize multiple dimensional data so that you can take projections both uniformly, so that the projection of any dimension has about the same performance, and also that you can choose subdimensions agilely. And this is really a distributed memory problem, not a computing problem. It requires very few cycles, but it's really memory inefficient. And so one of the principles behind Open CONNECTOME is to separate the data access side from the computation side. So what we do in Open CONNECTOME is come up with the views of the data that feed computational workflows. And that we don't provision a lot of processing because we don't do a lot of processing. Mostly what we do is shuffle data with some spatial database techniques like space filling curves. And that's a great offline conversation.
Cool, thank you.
Awesome. Let's thank Randal again. That was a great talk.
I like this slide because the Open Connect team just keeps growing. Lots of people in this room are on this slide, or some people in this room are on this slide. And the way to get on this slide is to come to Hopkins with data and work with us, and we love it. So please do exactly that.
Intersection of the two. And I guess I'm wondering, how do we bridge the gap between those two things? Which one sort of do we need more right now? And how do we think about, bridging between the two?
You're that guy.
I don't know if I'm exactly going to answer the question, but I'm going to say what I feel like saying.
Very reasonable.
The visualization problem, I mean, big data, we have a visualization problem. On one end, it's that we'll never see the raw data, and I was proposing statistics as a solution to that. On the other end, it's that we'll never see the result either, and that's kind of what Eve was getting at, because we're trying to characterize on a two-dimensional graph something that occurs in a very high dimension. And I don't know the answer to that. I mean, that's where you build the models, you do the reduced ideas, that's where it gets really, really hard. And again, I think this whole thing, whether all this methodology, it's an unusual time in neuroscience and when I think the methodology is way ahead of the ideas. And whether we catch up is going to just depend on whether we can look at the result end of the data in any way that makes sense.
Yeah, I mean, I think that, you know, we recently published a paper where we were trying to describe the behavior of 5 neurons, and my then graduate student invented a way of visualizing those 5 neurons all at once as a function of properties, and it was remarkable to be able to see, but she had to invent a new way of plotting the behavior of 5 neurons in order to reveal what was going on in the circuit. And that's 5 neurons. You know, I personally, now I'm old, I'm the oldest person in the room, I think, but I have a lot of trouble just by, yeah, but I'm older than either of these two guys, right? They're babies, but but I have a lot of trouble thinking in large numbers of neurons because I just can't imagine how to see what they're doing except when they're doing things like, you know, waves of activity flowing across the surface, or, you know, whole groups going into, you know, synchronous oscillatory modes and things like that. But if I try and think about, you know, 150,000 neurons all doing different things at different times, computing something like what these guys are worrying about, my mind just gets really confused. That's why I work on small numbers of neurons. I don't know how to think about those things. You.
So I certainly don't. I mean, and that's the visualization problem was one I complained about before. I mean, I think we've borrowed some tools that other people have developed so physics, for example, and dynamical systems. The idea that you can sort of think about the way that the nervous system evolves over time as being something akin to the way systems of interacting particles evolve with time. And the tools that people have developed to try and understand such physical systems have found fairly broad applicability in neuroscience. I've used some of them myself, and I've certainly admired other applications of them. I'm not sure what I understand when I see them, and I'm not sure I can tell the difference between something applied well and something applied poorly. I think the field has not yet established standards for interpreting and devising tools for doing this kind of stuff. We're all kind of fumbling around. Stuart Firestein, who many of you may know, has a book which I commend to all of you who aspire to be scientists called Ignorance and How It Drives Science. And Stuart begins his book by saying that science is sort of like looking for a black cat in a dark room, except you're not sure there's actually a cat in the room. And that's kind of the way I feel about a lot of the high-dimensional system stuff we're dealing with now. I mean, it could be that all of this stuff conceals the fact that there's actually no cat.
To pick up on and to belabor a point, to go back again in the old days, no, they were not all good, you know, right? There were many things that weren't good, you know, but there are lots of things that when people, the first person to put an electrode in a certain kind of neuron saw something and often recognized it. There were many times in my life where the first time I saw something on the microscope or on the oscilloscope, I said, holy, it was a reveal. You knew it. You understood it. You didn't need to do any data analysis because you saw it. The first time we stained for serotonin in the network and I saw the distribution of the serotonin immunoreactivity, I knew where it was and I knew what it meant. And that reveal, that moment where you have that direct connection, is something which surely will come when people do certain kinds of analyses and ask the right questions. But you have to have, I think as scientists, you have to know when you've seen something, you recognize it as telling you something that you didn't know before. And I think that's what makes us really enjoy doing science. Someone does something or you do something and you see something and you know instantly that you're seeing something that you didn't know before the other person or you did that. And that's what you have to make sure with all the new methodologies, that we retain that direct path to those reveals, however they come.
Yeah, I mean, it almost sounds like you're saying that all of the new technology for analysis and visualization, the real goal should actually just be getting us as close to the real data as possible, at least in a sort of
truth in the
to the
real
truth,
data.
right? Which is maybe harder to quantify. Well, guys, thank you so much. This was a really great discussion. Great to get your perspective. If you have any final words for this particular group of
Just keep going.
Yeah, this is all on you guys. So it's not going to be us who works out this stuff. And I think we should all give Jeremy and his gang a hand for putting this whole thing on.